right, welcome everyone to the morning session here in Vanderbilt. Our first speaker is Gazali Agboola. He's a PhD student at North Carolina A&T State University, and he'll be talking about landslide susceptibility in Western North Carolina using GIS and machine learning methods. And I don't think we have anyone online yet, but make sure your name's right if you are.
Good morning, everyone. Good morning to those online. Welcome to the presentation. I welcome everybody to this conference. As he said, thank you, Matt. My name is Gazali Agboola. I'm a PhD student at North Carolina Agricultural and Technical State University, and I'm working with Dr. Leila Ashemi-Benin of the Built Environment Department at North Carolina Agricultural and Technical State University. I'll be talking about landslide susceptibility. So as we all know, landslide is a general problem, is a critical natural disasters that need to be addressed all the time. So according to USGS, 79% of the landslides are triggered by heavy rainfall. But actually, heavy rainfall happens everywhere. But why are some areas so susceptible to this landslide? Why have landslide occurred in some areas and not other areas? That means landslide are actually caused. There are some factors that are actually leading to landsliding. So these are the factors that we put together to address this issue. Before I go, landslide is a critical issue, as I said earlier, and mapping susceptibility is like mapping the areas that are likely for landslide to occur in the nearest future. By taking the factors that are actually contributed to landslide in the previous time, we can actually predict which area will actually be susceptible to landslide in the nearest future. There have been some methods for landslide susceptibility. There are qualitative approach, that is manual interpretation of photogrammetry or aerial pictures, and inventory analysis. By looking at the historical landslide effects, we can actually determine whether there will be landslide in future in that particular area or not. And there are also semi-quantitative. We have analytical, hierarchical, weighted linear combination. Those ones are very common one. Weighted overlay, by considering the factors and overlay all of them to know which area are susceptible and which area are not susceptible. But the recent ones are also statistical analysis, like the information method, frequency ratio, weight of evidence, and due to complexity in computer analysis these days and the availability of remote sensing images, we have machine learning development for landslide susceptibility. The likes of extreme gradient boosting, random forest, linear regression, linear logistic regression, naive bias, and the likes of them. And also after that, there are still development into ensemble learning by combining different methods together, different machine learning together, and come up with a good one that actually increase the accuracy and the consistency of our predicted susceptibility. So in that case, we are going to make use, the study area is an area that is very close to this place. I think this is, if I'm not wrong, this is western part of North Carolina. So it's close to Asheville. So it's between the Polk County and the NDC County. So that's the study area we made use of. Actually, the reason for choosing this area is because landslide is frequent in this area. And there have been some studies about it from geological survey team. I've come across many papers from Wooten et al. And the likes of them. So, yeah, this is the study area. If you can see the red line, I don't know, it's not blurry on my laptop, but it's kind of blurry here. The red highlight, that's the study area. This is the Polk County, and this is the Edison County. This is where the study area is located in North Carolina. And we have the digital elevation model of the study area. The altitude ranges from 248 meters to 290 meters above sea level. Then the landslide inventory points data that we use is also overlaid on the digital elevation model. Please, in case you have any question as I'm talking, I think you can write it down, or if you have to point, please point and let me answer before we go to another slide. So that is the digital elevation model. The red signifies the high altitude, and the green color signifies low altitudes. Okay. Okay. The point is
so are these like landslide initiation points or what?
Okay, what a point does is the centroid. When the landslide happens, then it's find the centroid. That's what the point does. Yeah, the centroid of the landslide. So how did we source the data that we used? We got a digital elevation model from the USGS. It is approximately 10 meters in resolution. It is actually written there as 1/3 arc seconds. That's the resolution, but it's approximately 10 meters. Then geological map, we also got that from North Carolina Geological Survey team. Many thanks to them. And the resolution is 1 to 500,000. The land cover map was gotten from North America land cover 2020 using the Landsat. The resolution is 30 meters. The road characteristics from North Carolina Department of Transportation, and the distance from the stream is also gotten from NC1 map. NC1 map is a very powerful website by the North Carolina Information and Technology Management team. Then the soil map was gotten from United States Natural Resource Conservation Service. So how did we generate? We have the landslide inventory from NC1 map as well. So I think is the inventory map that has been generated by the North Carolina Geological Survey team. That's where we derive the point that I showed you earlier. But before we need to program this in machine learning, we need the negative side of it. That is, if landslide is serving as the positive, which is labeled as 1, we also need the label as 0. So that's where we apply 2 scenarios. That okay, there is no standard measure for getting this. So we made use of 2 scenarios. The first scenario is taking slope, the threshold of slope. That is, okay, we have known that landslide happens above this certain slope. Here we use 10 degrees of slope. That landslide happens above certain degree of slope. What if we consider 10 degrees of slope and below as area where landslide does not occur, so that we have the negative class of our model. So here we consider 10 degrees of slope. Another thing we use is buffer. That is, okay, a certain distance from previous landslide. Okay, we also have the slope. We must also be sure that the area we want to choose is also far from historical landslide. So we also chose areas based on slope threshold and also the buffer. Then the second scenario is, okay, some people said the first scenario, like if slope, we take slope threshold, that means we're already telling the machine or what to learn on. We're already saying, okay, slope is the major factor. Any area that is has a high slope categorizes as susceptible, and anyone below 10 degree categorizes as a non-landslide. That is why it is some people claim that it is subjective. So we now chose, okay, the second one is just buffer based only. That is, we only chose a distance of 250 meters away from landslide. So that's how we generated a landslide free point. So these are the factors. We make use of 14 landslide conditioning factors. The slope aspect, we show the direction where the slope is facing, the maximum slope where it is facing, the altitude, I've explained the altitude. The altitude is just the elevation above the sea level. Then the topography roughness index, topography position index. Those ones just measure the ruggedity of the terrain, the ruggedity of the topography. Then topography wetness index, the hydrological process. The hydrological process of the terrain is also measured by topography wetness index. And we made use of a plan curvature, the curvature, whether it is concave, convex, or flat of the slope is also considered. The profile curvature, distance from stream, distance from road is also considered here. We also consider the land cover map. We consider the soil map too. So this is the flow chart of the methodology. All these are the derivation of the landslide conditioning factors. The landslide conditioning factors are those factors that we consider as a factor that can lead to landslide, not a triggering factor. The triggering factor can be earthquake or rainfall, as I said earlier. So we generated the conditioning factor on ArcGIS Pro. So then we created a random selection of non-landslide points using the ArcGIS Pro as well. So then these are the factors that were considered. I said we did multicollinearity analysis. What does multicollinearity analysis does? It measures whether there is an interdependence among these factors. So if there is an interdependence among these factors, that means one factor is also leading to another, or one factor can be predicted from this. So this will create a redundancy in the modeling. So instead of that, we make use of VIF. VIF is various inflation factor. So it is a measure of interdependence among the factors that we consider. So if variance inflation factor is less than 10, then the interdependence will not really cause any issue. But if it is greater than 10, that means it's too high, then the factor has to be removed. Initially, NDVI and STI, stream transport index was considered, sediment transport index, sorry, was also considered here, but they were removed because the VIF was greater than 10. So when we did that, the factors that passed the multicollinearity test were taken for modeling. We divided the data into 80% training and 20% testing. And these are the models we make use of: support vector meshing, logistic regression, linear discriminant analysis, random forest, and extreme gradient boosting. Then we did ensemble methods. We use stacking and weighted average. Stacking is when we have model, the prediction of the models will be used as a data set for another prediction. That is, in order to get more accurate results, we use the model, we combine them together and create another, they call them, these are base classifiers, then we combine them together. When using the meta classifier, we use logistic regression for the stacking process. Then the weighted overlay It's like combining all the models together and give each model weight based on their performance. So that is how the weighted averaging ensemble works. Then we did the model validation. We used confusion metrics, ROC curve, and kappa score. Actually, this research, we made decision, we chose the best model based on ROC curve because landslide susceptibility uses threshold across all the points. Suppose we can use confusion metrics and overall accuracy, but those one they have a certain threshold that they want. But landslide susceptibility needs, you need to know which one is very low, which one is low, which one is medium, which one is very high, which one is high. So in that case, we make use of ROC curve, which can actually predict, which can actually measure across all threshold. So yeah, before we continue, we also need to know the effect of each class of all the factors versus the historical landslide. The first one on the list is the slope. If we all look at it, anywhere we have the frequency ratio to be very high, that means at that particular point, then landslide is the area that has that particular point, that particular class has a greater, has a very high susceptibility to landslide based on historical record. If we look at a slope, any slope that is greater than 40 degrees, we have 120 landslide there. And the area count, that is, the number of cells in that area is just 10,513. And we have the highest frequency from that class, which is 5.46. If we also look at 30 degrees, we also have the frequency ratio to be 3.84. If you look at it, any area less than 10, the frequency ratio is very, very low, which is 0.06. And that is the reason for our choice of the threshold that I explained earlier. So as the slope increases, the percentage of, the frequency ratio continue to increase. We also have the altitude. This is quite funny because where we have the higher altitude, like 800 to 1,290, the frequency ratio is quite low, it's very, very low. We have the landslide around between 400 and 800, which is the mid elevation range. And this is because at this level, it's just the formation, there are rocky formations which are not actually susceptible to landslide. And below the level of 400, is very close to flat area. There are no much landslide around that point too. We also have the aspect from northeast, east, and southeast, south. They have higher frequencies. Actually, according to some literatures, aspect is only considered because aspect has influence on so many factors, like the sunlight, the precipitation of an area. Where the slope is facing will determine whether the place will get dry quickly or it's going to remain overlocked with water. So that is why aspect is considered. We have the provide curvature, both provide curvature and plan curvature. Both of them are the convex and the concave level, this is less than 0.5 and greater than 0.5. Landslide is frequent there. Then at the flat level, where the aerial is flat, landslide is not very frequent there. Topography wetness index, as with the topography wetness increases, the ratio continue to also decrease. Stream power index, as the stream power index increases, the landslide increases as well. Also, the topography roughness index, the soil type, actually, based on geological survey findings, what I read on Wooten et al. 2022, they said there is no relationship between soil type and and the landslide. So, and the historical landslide that they don't have, they did not find any correlation between the two factors. Also, the land cover. We noticed that majority of the landslide occurred in the forest area. That is, I think those are the mountainous area. So that's why we have 1,072 out of 1,215 landslide considered in this research. They all happened in the forest area. The developed area is not also excluded due to the activities of women like road construction and the likes. And we also consider lithology. So we have lithology like the biotite genesis and the schist, then the other one that follow. We also consider the distance to road. The reason we have more frequency ratio like the distance greater than 800 is because majority of landslide occurred in the forest, which are very far from the roads. Actually, the one that occur close to the road are also they were disturbed by the roads construction, but the majority of landslide occurred in the forest, which are far from the roads. Okay. After building the model, we want to know which are the factors, the top 5 important factors that are actually out of the 14 that were considered in this study. We used random forest to get the importance of the factors. For scenario 1, this is why data selection is important, because the data selection actually have impact on the model. For scenario 1, the top 5 is slope, topographic wetness index, distance from road, altitude, and topographic position index. But for scenario 2, we have slope, altitude, stream power index, topographic position index, and the topographic wetness index. So based on this, we can actually see that in that area, the major factors that actually cause landslides are actually topographic factors, not the soil type, not the lithology. They are majorly topographic factors, because all the factors listed in scenario 2 are actually topography factor and geomorphology of the area. So these are the map that were generated after the whole modeling. This is what we did. We created data set. We use it to train the model. Then after the model is trained, we get the value of each factor for each pixel of all the landslide, all the study area. Then we predicted the predicted value based on based on susceptibility. We predicted each value. Then we extracted it from Python. We took it to, we digitalized it on GIS Pro. Then we generated the susceptibility map. Based on this one, the area highlighted in red, actually they are high susceptibility, and the green is very low susceptibility. Then it begins to come down like that. This is the susceptibility graph that were derived by support vector machine. This is for scenario 1, and that is for scenario 2. So then the graph we have down here is to show how many percentage of the study area were classified as very low, how many of them were classified as a low, medium, high, and very high. According to support vector machine, the 39% were classified as very low for scenario 1, and 46 were classified as very low for scenario 2, and 26 were classified as very high for scenario 1, and 9% were classified as very high for scenario 2. So these are the graphs for scenario 1 and scenario 2. And also, these are the graphs for logistic regression and linear discriminant analysis. You can see almost all of them, they have actually different classification. Actually, they are very close to each other, but they are somehow different. So this is both for both scenarios. And this is for random forest, and the other one is for extreme gradient boosting, XG boost. And this is the weighted average and the stacking. The best accuracy came from the weighted average, and the area that were classified as very high for scenario 2 is 9%, and scenario 1, 27% were classified as very high. Yeah, this is the ROC curve. According to the ROC curve, the weighted average that gave the best performance in scenario 1, we have 99.4% of accuracy. And for the scenario 2, we have 91.8% accuracy. That means scenario 1 gave the best accuracy based on threshold, slope threshold. So this is the performance assessment metrics. We have the overall accuracy. We have the kappa score. What the kappa score? The kappa score is between -1 and 1. If it is -1, that means the model is performing so badly. If it is close to 0, that means the model is just making guess. But if it is above 0, that means the model accuracy is high to some extent. So according to the kappa score of scenario 1 is very high. We have the highest kappa score coming from extreme gradient boosting at 92.2%. And for scenario 2, we have the weighted average. I mean, we have the logistic regression at 65.3 accuracy, which these are great group. I mean, the model perform very, very good. So then we also have the confusion matrix. What the confusion matrix shows is that out of the test data that we used, when we test the data, when we validate, how many of the landslide that were truly positive were classified as truly positive, how many of them false positive, how many of them were negative, then they were classified as positive. Then true negative, how many of them were actually negative, they were also classified as negative. Then precision measure that out of all the positive classification that we have, how many of them, what is the percentage of actually the positive, that they are truly positive? That out of the landslide that they were classified as being landslide, how many of them are actually landslide? Then the recall is out of the positive landslide that we have, how many of them were actually classified as positive? Out of the positive that we have, many of them are actually classified as positive. And in order to create balance, that's what the F1 score does. That is the harmonic mean between the two to get if we want to actually measure the performance of the model based on confusion matrix, we make use of F1, which create the balance between precision and recall. So here we want to see we want to use the sky metrics to measure the consistency and to measure the consistency of our map. Are our map consistent, or are we just is it just the accuracy? Is it just by luck? So we try to what the sky index does is the percentage of landslide, then the area, the percentage area. So this thing actually is supposed to be decreasing. That is the sky index supposed to be decreasing. That is the sky index seed cell area index. That is it's supposed to be decreasing. If there is a point that there is no decrement, then the model is not consistent or the scenario is not consistent. If we look at extreme gradient boosting, SG boost, at this point, we actually have inconsistency. because we have 4.47 here, then we have 4.85. It's supposed to decrease, but here it increased. So the extreme gradient boosting in scenario 1 was the only model that gave us inconsistency. All other models and scenarios, we have consistency in that area. So we also want to know the relationship among the models. Are they related? Are they very close to each other? We noticed that linear discriminant analysis, logistic regression, and support vector machine were very, very close to each other. Then the weighted average ensemble is very close to all other models. So in conclusion, it's all discussion. I think my time is almost over. So from the frequency ratio table, we have that slope is a major factor. There are no other topography factors in this in the area. So then the Lake Law and the Green River, the two regions, the vicinity around that area were classified as a very high susceptible to landslide. The Lake Law area and the Green River area. So this is landslide. The Howard Gap Road area too were classified as very susceptible to landslide. This is the landslide that happened in 2018 that devastated the Howard Gap Road. So because of time, these are the references. Let me quickly rush, and I would like to give thanks to my advisor, Dr. Leila Shemibeni, the North Carolina Geological Survey team. I don't know if they were, Bozdog is here, Nick, and Dr. Taylor, the North Carolina Emergency Management team, Gary Thompson and Ross Watson for providing us with data. Many thanks to them. And the research is sponsored by North Carolina Department of Transportation. Thank you.